using Ampere circuital law, we are going to find the magnetic field. Magnetic field of a straight conductor, current carrying conductor, and thick current carrying conductor, and finally solenoid. So 3 questions we have as a direct question. So see the straight current carrying conductor, it is very easy. Okay, thick conductor we have some derivation, and solenoid also it is easy. The similarity is Ampere circuital law is similar to Gauss law. This case is similar to Gauss law. What is Gauss law? Do you remember?
Yes, sir.
The line, the surface integral of the electric field over the surface is equal to mu naught, not mu naught, Q enclosed divided by epsilon naught.
Yes, yes, sir.
Yeah, this is what Gauss law. Okay, they have given it as phi equals to Q enclosed by epsilon naught, but actually phi is expressed as a surface integral. Okay, the surface integral of a closed surface integral of the electric field, it is equal to the charge enclosed divided by epsilon naught. So similar to Gauss law, we have Ampere circuital law. The main applications of Gauss law is to find electric field of various objects or shapes. Various objects. The main application is it is very easy to find the value, very easier. Similarly, Ampere circuital law, it is alternate of Biot-Savart law. Here also Gauss law simplifies Coulomb's law. Similarly, here Ampere circuital law, it simplifies Biot-Savart law. That's all. So now we'll go for the statement. Statement is the line integral of the magnetic field around any closed path is equal to mu naught times the current enclosed times total current enclosed through the path. So this is the statement. Okay, it is again similar. See in here the only difference is here it is line integral. The previous case it is the surface integral. This one is surface integral.
Okay, sir.
Or it is the area. It represents the area, but here it represents only the loop. Okay, only the line. Okay, it is a length. Therefore, the formula here it is integral P dot dl. So instead of ds, you just go for dl. The closed integral, which is equal to mu naught I enclosed. That's all. See, everything remains, it is equivalent terms. Here it is E, here it is B. And the mu naught, epsilon naught. And current charge. That's all. So the source of electric field is the charge, the source of magnetic field is the current. Okay. See this loop. So in the previous Gauss law, no, we studied Gaussian loop or Gaussian surface, not Gaussian loop, Gaussian surface we studied. Here we have another imaginary length, Amperian loop we will study. Okay, now our first application is to extend to find the application. This first question, straight current carrying conductor. To find the magnetic field due to the straight current carrying conductor, that question is. Due to conductor. Using Ampere's law. We have the current carrying conductor having current I. And we know the magnetic field due to a current carrying conductor, it is a concentric circle. Okay, we have a circular magnetic field threading around the current carrying conductor, and we know the direction. How to find the direction? Again, right hand curl rule. Right hand curl rule in the opposite direction. Okay, right hand curl rule or right hand rule. If you hold, okay, just hold the current carrying conductor in the right hand. If you hold the current carrying conductor in this manner, the thumb represents direction of current. Then the curled fingers, they represent magnetic field, direction of magnetic field. Direction of magnetic field. For this case, the magnetic field will flow in this direction. Okay, they flow in this direction. Okay, at any instant, if you want to take the direction of magnetic field, it will be perpendicular to the radius vector. Suppose the distance from the conductor, if it is r, so it is perpendicular to the radius vector. So this is the direction of magnetic field, and the r is perpendicular to it at that particular point. Now what we are going to take? Now we are going to take a small element, small portion of the loop. See, for this circular loop, no, it is not current carrying loop. We have to be very careful. It is not current carrying loop. It is only the representation of the magnetic field, the direction of magnetic field. The current carrying wire, it is a straight wire. Okay. The direction direction of magnetic field at any point is the direction of the tangent at that point. So that is what I said. At this particular point, if you take a tangent, the direction of the tangent is the direction of the magnetic field. We know the direction, the tangent is perpendicular to the radius vector. Okay.
Yes.
Now, and another one point, the magnitude of magnetic field at any point on the loop is the same. Why? Because the distance is same and the angle at any instant, the angle is also the same. Therefore, there will be no change in the magnitude of magnetic field. So throughout the circle, the magnetic field remains same.
Oh, okay.
Therefore, using Biot-Savart law. Therefore, using Biot-Savart law, the magnetic field due to a at this particular small element dl, okay, it is not current carrying element. This is a length element. Okay, only the small portion of the circle or the loop, which is equal to mu naught I enclosed. Okay, the current I is enclosed in this particular loop. Okay, and magnetic field already we said it is same. It means it is constant. You just take it outside. B integral dl. The integral dl. One more thing I forgot to mention. Actually, it is a dot product. Dot product. Therefore, it is integral b dl cos theta. If here it is 0 degree, it is 0 degree.
0 degree.
Actually, the theta is angle between P and dl. Okay, don't confuse with the r vector. Angle
So
between B and dl. dl again it is the tangent. B it is also tangent. Both are pointing in the same direction. Therefore, the value theta becomes 1, and we are going to take the B outside and mu naught I enclosed. Here enclosed current is only I. Okay, and integrating the loop over the length, it will give us only 2 pi r. So B into 2 pi r equal to mu naught I. Therefore, the magnitude of the magnetic field is equal to mu naught I divided by 2 pi r. That's all. Next question is thick conductor. Okay, this question it is given in your NCERT example. See, this one, long straight wire. Okay, long straight wire, but the question is the current distribution is something different. Okay, in the previous case, in this particular question, no, this question it is a thin, long, straight current carrying conductor. Okay, there is no distribution of current in the area of cross section. The area of cross section is almost negligible. At the center, the current is something different. Along the axis of the conductor, see this diagram carefully. See, we have a cylindrical cross section, area of cross section. Okay, along the axis, the current is having different value. Okay, as we are going away from the axis till the surface, the current keeps on increasing. at the surface we are getting the maximum current value. Okay, we are going to find the magnetic field outside and inside. The two cases they are given. So it is not similar to the previous case. Previous case, we have only one situation. On the outside of the conductor, we are measuring. But in here, we are going to measure inside also. Carefully, you see the question. R is less than A, R is greater than A. Okay, we will first go for R greater than A. First, R greater than A. R is greater than A, I'm going to solve the very beginning. Because this case is very easy. Consider this diagram. So your current carrying conductor, and this is axis. And the point, see the radius of the conductor is capital small e. R is the point outside. It is located outside the conductor. From the axis, the point R is located outside, which is greater than A. Okay, at this particular point P, we are going to find the magnetic field due to the entire current carrying conductor. Okay, it is similar to the previous case. Same answer will come. Therefore, the magnetic field outside, be outside the conductor, which is equal to integral B dl equal to mu naught I. Therefore, B is equal to 2 pi A mu naught I. Answer is B equals to mu naught I divided by 2 pi A. That's all. For this particular question, for this case, R is greater than A. The answer is simple. Do you understand?
Yes, sir.
The answer is very simple. Suppose if you see this diagram, the point outside it is given small r. It's given r, small r. Inside it is given r1. Loop L. Okay, depending on the given data, you can go for the derivation. So if I use this particular case, no, I'm going to include it as loop 1. Okay, so loop L, capital L, and instead of A, I have to use R. So no problem. No problem in this case. Wait. I think I made a mistake. See here, I have taken A. No, it is wrong. It is R only. Because we have taken the entire loop, the circle, so the radius is R, not A. So this R only. Okay, so this R only. So both the diagrams, they remain same. Okay, now the second case, the point is inside. The point is inside, see L1, loop L1. Here the distance R is less than A. R is less than A. See, in this case, we draw the diagram little bit bigger. This is our axis, and the radius is A, and the point is lying inside. The point is lying inside. The distance is R. What happens now here? The current is not the same. At the point inside the conductor, I becomes I dash. It becomes I dash. Why? Because the current is uniformly distributed. I is uniformly distributed. It means the current density remains same. Current density remains same. Therefore, outside the current density is I divided by pi a square on the surface, not outside. On the surface, the current density is I divided by pi a square. In the interior, I dash divided by area is pi r square. Do you understand?
Yes. Okay. Yes, sir.
Now, in this particular case, I dash become pi get cancelled. I r square divided by a square. This is the current enclosed. I enclosed inside. The current enclosed inside the Amperian loop is I r square divided by a square. Therefore, integral b dot dl equals to mu naught I enclosed. Take b outside. Integral dl becomes 2 pi r. It becomes 2 pi r, and mu naught I enclosed is I r square divided by a square. Here r and square they get cancelled. R and square they get cancelled. Therefore, b equal by 2 pi a square. Two pi a square. Here b is directly proportional to r when r is less than a, but for this case b is inversely proportional to r. For first case, r is greater than a. When r is greater than a, b is inversely proportional to r. When r is less than a, b is directly proportional to r. From the center, the current keep on increasing linearly.
Okay.
Okay.
Yes.
Okay, so that's that. This is the answer, and we have another situation. The graph for this question. For this question, we have a graph also. I just remove this diagram. Okay, take distance in the x-axis and the magnitude of magnetic field in the y-axis. R and B. Suppose you just consider this as the radius. Radius small r. So radius small radius is A. Radius is A. From the center, the magnetic field keeps on increasing. Magnetic field, it keeps on increasing till the value reaches the surface. Okay, at the surface, the value is maximum. B is maximum, and then it decreasing. It keeps decreasing by 1 by r. Here it is B proportional to r. Here B is inversely proportional to r. That's all. Here is the maximum value. At radius A, the magnitude of magnetic field is maximum.
Okay, sir.
Okay, but actually I forgot to mention the Amperian loop. The Amperian loop is, in this case, this one is the Amperian loop, and here the Amperian loop is the center red color circle, similar to our Gaussian surface.
Oh, okay, sir.
Next is the solenoid. The application, the third application is the solenoid. Magnetic field due to a current carrying solenoid. We know a solenoid having n number of turns, n number of turns, and L is the length of the solenoid, and small n is the number of turns per unit length. Number of turns per unit length. So we need to understand small n as well as capital N. Small n is number of turns per unit length, and capital N is the actual turn, number of turns. Okay, here n is per meter. Unit of n is per meter, otherwise meter inverse. Unit is meter inverse. But for capital N, it is just number, there is no unit. Like 100 turns in 1 centimeter, or 50 turns in 1 centimeter, like, or 4,000 turns in 1 meter. Similarly, we will get.
Okay.
Actually, what is a solenoid? It is a closely wound. Solenoid is a closely wound coil of n turns. A closely wound coil. See, the magnetic field due to a single circular coil, it is something different from a solenoid, current carrying solenoid, because here the shape is entirely different. See, actually, the wire is insulated wire. Insulated wire. It means that for each turn now, if the wire, if they are touching if one particular circular coil it is touching each other, it will not produce any contact. So that is why we go for insulated wire. The specialty is, as the current go into the solenoid, no, it produces a magnetic field inside the solenoid as a straight line. See, the magnetic field due to a solenoid inside is uniform. It produces uniform magnetic field, and outside the magnetic field is almost, it is zero. Outside
Yes,
is
sir.
almost zero. So inside it is magnetic, inside it is uniform. It is like a uniform magnetic field. So the magnetic field value is V equal to mu naught Ni. That's all. The magnetic field due to a solenoid is mu naught Ni. This is what we are going to calculate. Okay, we will see one by one how to measure the value. Solenoid, we have another name. It is a what is that? Inductor. We'll study in electromagnetic induction. Inductor.
Inductor.
Both are same. See, and one more thing, solenoid is a coil. It is a coil. But not all coils are solenoid. Okay, it is a coil, but a coil it is not a solenoid. It is a type of coil. That is why I said it is a closely wound coil.
So sir, if it is if any wire is wounded around the surface, so it won't be a solenoid, right? Like if it's in the same structure.
Yeah, suppose if the it may be a coil, rectangular coil or a squared coil. Suppose if you have a what is that? This kind of arrangement. If you wound a wire, no?
Yes, sir.
Yeah, it will also act like a solenoid.
Oh.
Okay, it is like a rectangular coil. Suppose see this one becomes a solenoid. This one becomes purely a solenoid. But we have a special kind of rectangular coil in galvanometer. The galvanometer, a coil is wound in this manner. Okay, like a rectangle, we will wound. Okay, but the length is it will be very small. Length will be very small in that particular case. But this one, it is similar to solenoid only. Okay, now come to the point. So next, the aim is to calculate the magnetic field at the center. Okay, inside the solenoid, what is the value? So that is what we are going to find. See, we have a standard diagram for this question. See, this is the solenoid, the magnetic field. So inside it is parallel, but at the edges, no, there may be some deviations.
Okay, sir.
Okay, at the ends of the solenoid, there may be some fluctuations. Okay, see, this is what we are going to use. See, this is the cross-sectional view of solenoid. Okay, if you have a we if it is closely wound, no, we will get a solenoid as a cylinder. Okay, it will be in the cylindrical shape, and we made a cut. As a cross-sectional view. Nothing is available. Okay, you just see the cross-sectional view we are seeing. Okay, the dots represents the current comes out, and the cross mark current goes in. Okay, in out of the plane of paper and into the plane of paper. Okay, at this particular point, current is pointing outward. Okay, actually, suppose if you connect a wire, a solenoid, it comes in this direction. Okay, actually the wires are not shown. The current, it is coming in this direction. Okay, that is why they are using the dots and cross marks. That's all. Okay, see, in this particular case, we are going to find the magnetic field in the interior of the solenoid as well as the outside using Ampere's law. Using Ampere's law. Okay. Okay, so now to find the magnetic field inside, consider rectangular closed path ABCD. See, we are assuming an imaginary closed path ABCD in this case. So, wait a minute. Okay, so rectangular path ABCD has an Amperian law. Amperian law. Therefore, using Ampere's law, the line integral of the magnetic field at this particular loop ABCD, which is equal to mu naught I enclosed. Okay, the total current through the enclosed surface. Okay, but in this case, see, we have four different segments: AB, BC, CD, and DA. They are not identical. Okay, and the magnetic field at each loop is different. Okay, in the previous case, what we did know, in straight current carrying conductor, we mentioned that the magnetic field at every point is same. Okay,
Same.
every point is same, but in this particular case, it is not same everywhere. Along AB, it is one particular value, and CD BC, CD, and DA, everything is different. Therefore, this particular integral equation, no, it is split into four different equations. Therefore, integral B dot dl is split. Integral B dot dl is split into integral A to B dot dl plus integral B to C B dot dl, then C to D B dot dl, then D to A B dot dl. So we have made four different integrals. Now we are going to calculate the magnetic field due to the each segment. Okay, here the important thing is CD is lying outside of the current carrying loop. Okay, no current is enclosed at this particular point. Actually, current is enclosed in this particular direction. Okay, the current is not enclosed in the loop, sorry, in the segment CD.
Yes,
We
sir.
know, I already told you know the current is pointing in this direction. Okay, the
Yes, sir.
current is not at all enclosed. Okay, at the point CD, current is not enclosed. Okay, CD current is not enclosed. It means that this particular integral is equal to 0. This becomes 0.
Yes, sir.
And BC and DA, the segment BC, suppose this is DL, no, if you consider this as DL, and the
Yes.
magnetic field, it is in this direction. Magnetic field, it is in this direction. So the
Yes, sir.
angle between DL and B,
Oh,
okay, for the segments BC and DA, theta equal to 90 degree. Theta equal to 90
nine.
degree. It means these two integrals. What are those three integrals? BC and DA also 0. So the only remaining value is this one,
Maybe.
DL. See this case, DL and B in the same direction. Therefore,
0 degree.
theta 0 degree. Therefore, our desired value integral B dot DL A to B equals to mu naught I enclosed. And solving this integration, okay, integral we know theta equal to 0 degree. So integral B dl, which is equal to mu naught. Here enclosed current is due to the n number of turns into I. You have to be very careful. Okay, enclosed current is n number of I, n times I. So be very careful. And the integration, it extends from 0 to L. So here L is the length of the solenoid. L, length of the
Solenoid.
solenoid. And N is the number of turns. Number of turns.
Oh,
Okay, if you integrate this one, it becomes BL, which is equal to mu naught Ni. And take this L to the right hand side, B becomes mu naught N divided by L into I. As we told already, NL becomes small n. Therefore, it becomes mu naught Ni
okay.
because
Okay, sir.
n by L is equal to small n. So this is the answer. So B equal to mu naught Ni.
And
That's all. Actually, the question is very simple. Okay, but we have to explain the things. So we are considering an Amperian loop from A to D. Okay, here B and C and D and A, they are opposite. Also, they have 90 degree. Okay, there is no magnetic field enclosed in the two loops. Also, CD, it lies outside of the solenoid. Therefore, magnetic field is very less. So it is almost zero only. The current is not enclosed. So that is why it is taken 0.
okay, sir.
See, practically, if we see, no, it is not exactly equal to 0, but the value is very small. Okay, it can be ignored. The presence of magnetic field at this particular point, the Q, already they have mentioned, no, the Q is, it is almost 0. So it is not exactly 0, almost 0. The value is very less.
Okay, sir.
Okay, so this is about the magnetic field due to a solenoid. Okay, and here also we have a graph for this particular case. We'll draw the graph in the previous page. See, magnetic field B, inside is mu naught Ni, and ends end of the solenoid at this particular point, end, at these two ends, the value will become half of the actual value. Okay, it is half the times mu naught Ni. Okay, just keep in mind.
Okay, sir.
And we have a graph. So this one is center of the solenoid. Okay, center of the solenoid is, it is at this particular point, center, and length. So L by 2, L by 2, end of the solenoid. Okay, half the length, L by 2. Okay, half the length. L minus L. So this value, suppose if I take this as half the value, minus L by 2, L by 2. So the value becomes maximum at this particular point. From this particular point onwards, it becomes half of the value. Okay, so this is the graph of the magnetic field due to a solenoid. So here it is maximum value, and here it is B by 2.